Everyone, January 28th. All right, let's do it. Redundant connections. Ooh, gateway timeout. Interesting. Oh, old problem. A tree is an undirected graph that is connected and has no cycles. You are given a graph that started as a tree with n nodes, label 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge that already existed. The graph is represented as an array of edges. Then there is an edge, Return an edge that can be removed so that the resulting graph is a tree of n nodes. Return the answer that occurs last in the input. So among the edges, one of them can be removed. By removing it, it will become, it's connected and has no cycle. So basically we need to remove the edge that make it into a cycle, right? Make it into a cycle. Make it into a cycle. So it must be an edge that's in the cycle. So what we can do, we can try to find a cycle first, right? How do you find a cycle? Now you start from any node and then you just keep going until you reach it again. Then that is the cycle. Right? So like if I start from here, I go like BFS. One of the BFS will hit it again. Then we can return that what's an easy way to find a cycle? I mean, I know I have that's probably not the best way to find cycles. Just just DFS it. That's okay. Just DFS it. We find something, and then it will loop around. It will hit, right? And once it hits, we can mark it, or we can just escape. We can get out. Well, the question, maybe there are more than one cycles though. Can one edge? Now it does say you can remove multiple. In this case, you can remove multiple edges, right? Let's see. We have 1,000 nodes. No repeated edge. So basically, the question is, which edge we remove will make it not a a cycle. So I think we probably can brute force this. We just remove an edge and then just go through it and see if we can hit all the nodes, and then and it should take, so O(n) squared, right? O(n) squared will work. We just remove one and we do it. We remove another one and we do it. One of them will make it work, and then we'll call it like that. Okay, so that's one way. Is there a method that we can do to not brute force this? Well, if you want to not brute force it, you then you're looking for an edge, right? You need to look for an edge. And yes, you can look for the cycle, but there may be multiple cycles, right? There may be multiple cycles. So you go through, and maybe there are small cycles, and there may be big cycles, right? How do you distinguish that? Right? You might hit a cycle, and then you identify it, and then you try another one. It might be another cycle. But the thing is, originally it's a tree, right? Originally it's not connected. I do not think, given a tree that's not connected, you add one edge, right? You add one edge. I think at most you can create one cycle. That is my belief. At most you can create one cycle. I don't think you can create two cycles by just adding one. Because if it's a tree, right? If it's a tree, you will have, like a typical tree is just undirected graph, right? A typical tree like this, it's not really necessarily to be binary, so you can actually have another one, you can have 4, doesn't matter, you can have whatever, but the point is, if you add one edge, only one, right? You add one edge, then at most you can create one cycle, because initially nobody else, there's no cycle, right? There's no cycle initially, and you add an edge, then you create a cycle, right? Because you add an edge, you create a cycle. Now our job is to find this, which I think we can do using DFS, right? We'll find this, and or maybe we can do that. Oh, how can we do? Because when I find this, I start from anything. Go, 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 boom. I find it, right? I say I have a cycle. And once the cycle is out, I can actually unwind, right? I can unwind. I can keep track. And save it. Right? I can save it in an external variable. All right, time to do important stuff. Oh yeah. Now we can certainly we can certainly find this this thing. But then the question is, how do we find the last? Because we have a lot of nodes here, have a lot of paths here. So we'll have a path, right? And then we can go each pair. We need to check its position. How do we check its position? Now we have to get a pair. Then we need a map. All right, let's see if the probably solve this in two methods. One is the first one will be, let's see, this will be the brute force, right? And we do need n is edges length. Okay, so we say and then we need to create a graph, because this is not, right? This is just tell you, yeah, this is not. So we need to create a graph. Oh, yes, vector. Say graph and vector. Yeah, right. Say for E of edges, we can say graph E0 dot append dot pushback, and then graph E1 dot pushback E0, right? Okay, and then we, how do we, yep, that's not a vector, that has to be a set. That has to be a set. Insert, unfortunately. Hey, if you put insert, set. Right, and then we can go say for int I equal to n minus 1, I large equal to 0, I minus minus. Okay, remove edges I. How do we remove? We say graph graph edges I. I'm gonna say int a edges I 0, b edges I 1, right? And then we can say graph a dot erase b, graph b dot erase a, and then we say DFS. Where do we start? It doesn't matter, right, where we start. Yeah, it doesn't matter, we just start from 1. So we DFS is basically we just to try to see if we can find. So two things. We need to see if we can find, and we need to see if we can what will be the easiest way to check? Well, we can always do another set to put it in. Right? And we say if it's in it, then we'll return false. Right? True or false? Like true will be there's no cycle. false will be there is cycle, but we also need to keep track of, we can say std set visited. All right, now we say visited and probably do graph first. Graph and visited. If it's true, that means has cycle, right? Wait, don't say it. Has cycle. Has cycle. Right? If it has cycle, then if it does not have cycle, right? If it does not have cycle and visited dot size is equal to n and is connected, then this is the one. Then we shall break. No, then we shall return edges I. Otherwise, we will put it back, insert B, and graph B, insert A, and return what do we return? std vector should not reach here. Alright, now we just need to say has cycle. Boolean has cycle. We have a node, we have vector, graph, and set visited, right? If visited dot contains node, return false. Okay, otherwise visited dot add insert node, right, for int child of graph node. I need a parent as well, because I'm not going back to the parent. It's my next one, right? I do need parent. So parent, I do need parent. If child is not equal to parent, then and has cycle child parent is node graph and visited. Has cycle. Now this is true. So if it, and this is true, then we return true. Alright, otherwise we could go through everybody. Once we go through everybody, then we shall return false. Okay, so this one needs a parent. I can just do the 0. There's no 0 in this. What? Cannot bind a, wait, what? Ooh, my bad, I forgot. I changed this set. Alright, wanna try? Give this a run. See if it works. That is expected because it should be +1. Damn. I forgot. I should be +1. Yep, looks good. So we call it brute force. $684. Since the size of edges is not more than 1000, we can brute force this by removing each edge from right to left and check whether the remaining graph is connected and has cycle. It's absolutely O(n)² squared. Alright, we'll give this a run. See how it goes. Yeah, I expect it to pass. 8 milliseconds, 15.35. Alright, so now the brute force works. We should think about how to do it directly. Right, so we need the kind of solution 2. Yeah, let's do a solution 2. So in this solution, we are going to let's find. Okay, it is my educated guess that given a connected tree, adding one additional edge can produce at most one cycle. Thus, we can DFS the graph to find a cycle and then see which edge in the cycle appears the latest in the edges array. Okay, so this is kind of the idea behind this. So we'll do the edges first. We probably use a different data structure than this. Right, we'll use the different data structure. So what we're gonna do is, instead of a set, we'll use a vector. Okay, and oh, this is also not a set, it should be a vector. And here, instead of insert, it should be pushback. And this shall be pushback as well. Alright, so we got the graph, then we need a DFS, and we can, at the end, we can actually just return it, a vector. Right, we can just return a vector. We'll return the indices. Index. We return the index. Very good. Because we'll have somebody in it, right? Then, yeah. Okay, so we need index. So edge indices. How do we do it? Edge indices. So we can do a n by n. I wonder if there's a better way. Edge indices. Or can I? That's probably not going to work. Let me think again. Okay, let's try. Let's say a map, right, of a pair, right, and int edge indices. Probably need to do map. Okay, and then we can say map E0, E1. Oh my goodness. That is not gonna work. Okay. Why? Say A. Yeah, and then we do this. A. Okay, then we say B, B, and AB equal to I, map BA equal to I. I guess we cannot do it this way. Wait a second. Oh, it's not map. It's called edge indices. Right, so we got edge indices done. And then we call darn, we need two things. Okay, we're gonna call it DFS1 parent. Right, one parent. We need to have graph. We have edge indices, path, and this path should just be a vector of int, and we need a visited. What's visited? Set. Index equal to this. Turn edges index. Alright, so now let's try this one. Int DFS node parent vector of int graph map of pair edge indices path visited. Okay. If visited dot contains node. Right, this is what we're gonna do. So what we're gonna do is for the path, go right to left on the path, right? Because I know just right to left until we hit. Okay, so for int I equal to path dot size -1, I large equal to 0, and we need to get because I need to get I -1, right? So I actually should be larger than 0, and path I is not equal to node, right? Because node is the and. So if the current is the node, then we have trouble. This is not. Actually, I think we have a cycle, so I think this is sufficient. I minus minus, right? And we say auto edge make pair, right? Make pair, what we're gonna have here is going to be path I and then path I -1 if edge indices dot edge not equal to edge indices dot end, then we'll return edge indices edge, right? That's what we're going to return. Otherwise we'll return -1, right? This should not reach here. Okay, this is if we find a cycle. If not, then we say visited.add.insert node, right? We'll put the node in. Come on, node. And then we'll go through for int child of graph node. If child is not equal to parent, index shall equal to DFS child parent graph edge indices path and visited. Oh, and then path dot insert push back node. If index is logical to 0, return index. Otherwise, we keep going. Otherwise, yeah, otherwise we keep going until we finish. Then we shall say path.pop back. Actually, I'm not sure. No, I think it's fine. And then visited.erase node. So this is like a backtracking, right? This is backtracking here. Which I don't think is necessary, because we'll just keep going, and then we'll always find. Do we need to do this? Do we need to backtrack? Well, because you're putting it on the same path, right? So you push it back, and then we keep going, and then if and a certain route you hit to the end, right? Then you do need to unwind. Yeah, you do need to unwind. Unfortunately, we have to unwind. Okay, and then we'll return a -1. Right, so this is also should not reach here. But if it doesn't reach here, it shouldn't reach here either, right? I think it will reach here. Like I said, if it's yeah, it will reach here. So now we have DFS. Right, now we have DFS. How do I get cannot bind to a temporary? Well, I guess let's just not kid ourselves. We can just do this. Set visited. Right, and then we just do path and visited. Okay, let's see how this one works. I expect good results out of this. Unfortunately, it is not correct. I have no idea why. Output 1, 2. Oh, I didn't. Oh, you did not get. Holy crap. No, that's not right. Oh, yeah. Here. This is not right. You do this mapping, it doesn't really work. It will always be inside. You don't know which one is the dude. Okay, yeah, this is a different problem. So I have a bunch of edges. How do we know which one occurs at the latest? Ah, I see. Yeah, this is not right. So, so we're gonna go this pair, right? And we shall say the index equal to -1, right? Then we shall say index equal to std max index and edge indices edge. Yeah, and then we will return index. I have no idea why I was not able to do it earlier. This looks very straightforward and I completely miss it. You need to find a maximum. Oh, wait, this is still not right. But I went through every single pair, didn't I? I'm trying to find the maximum. Huh. This is interesting. I'm returning the same result. Okay, so let's take a look at path. How do I print path? I don't know. One, two. What the hell? Oh, type this one wrong. Should be node. There we go. The first one is right. 1, 2, 3. We got 2, 3. The second one is not right. 1, 2, 3, 4. Right? 1, 2, 3, 4. Ooh, that is correct. Yes. So basically 4 to 3, 4, 3, 3, 2, 2, 1, and then we need another one. Right? So we shall say std max index and edge indices indices at the end. It shall be path. It shall be node, right? So node and the end of the path. Path dot size -1. That shall be right. Yep. So we're gonna delete this one and make a comment. Don't forget the edge connecting the end of path to the current node. To the start, to the cycle, right? All right, we'll run it one more time. If everything good, we're gonna submit it. I think this one shall run in ON time. It took ON to do all this. DFS also take ON. All right, let's try it. No, it's not ON. What? It does say it's ON, but my previous submission is also. Ooh, I can do one per day. All right, I don't know why both are 8 milliseconds. I feel like this is should be much faster, or not? Oh, I mean, the worst case scenario that, yeah, so you go to all the paths, and then you hit this, so you do, yeah, that's still not O(n) squared. I don't know. What do you think? This is brute force O(n) squared single traversal. Yeah, it should be O(n), right? I believe this is O(n). That's what I believe. But we do need to have this backtracking, and I don't really quite like the backtracking idea. Well, it has backtracking because you're keeping track of, but here is using what? JCC is fine. Visited, what's visited? It's a Boolean value, and it has a parent. And then we go through the parent, right? Yeah, node equal to parent. You see that? Cycle start. What is cycle start? Dude, what is cycle start? Huh? Oh, they use a global value. Okay. Oh well. I mean, that's alright. Yeah, that's alright. So it's a cycle start. And then start from cycle start, backtrack to get all the nodes in the cycle, mark them on the map. Yep. And then you will go through everything, all the edges, and then you find if both, then you return. Yeah, it's the same, but I don't know. Data structure wise, maybe it's faster. All right, this is union find, right? So union and find, you basically, oh, union and find. Ah, okay. So union and find, yes, your union. So basically, if a pair is already in the union, then you can stop. Okay, so a pair is already in it, so you go, huh? Yeah. So union find, you just put everybody in it, right? You put everybody in it, and now hold a second. Put everybody in it. It should be if you remove something. Hold on. So you put in, and then you try to add the next one, right? And then try to add the next one, and one of them you add, it's not. Like you added it, then it become So you add from left to right then. Right, you add from left to right, and the first one, oh, I don't know. You add from left to right. And how you make sure that oh, it doesn't matter, right? You just keep adding. Like if nobody has, then you can just keep going. So what if the last one does? Ah, yep, makes sense. Union find makes sense. I think one day you have to do union find again. Otherwise, you're gonna forget how to do union find. Well, we can see. Maybe we can, if you find, if basically it's a current node's parent is equal to current node, we return it. Or if current node is not equal to, then we will say current node's parent, where you go to find the current node's parent. Yes, and then we'll return that. Okay, that's fine. The union is we'll find both parents. If it's equal, then we, whatever you want to say. If it's not equal, then we have a rank, right? We'll do the higher rank. We'll assign it to the higher rank. Yeah, I think I can write union find. All right, that shall be it. That shall be it. I mean, these days, each problem I use like 2 methods or stuff. It always take a long time to get through. All right, that'll be it. See you guys tomorrow for the next problem. We are 1671. Okay, so we're getting closer. We only have like 300 days left. 329 days. Another year. Next year around this time, around New Year next year, I think we'll get it. In fact, in like 329, I'm actually curious. What date will it be in 329 days? Wow. December 23rd. It's this year. It's this year, baby. Christmas Eve this year. That's when we'll hit 2000. This year. All right. Can't wait. Can't wait, man. All right. I'll see you guys tomorrow. Adios.